Our next and last speaker is Yves Fauser. He will talk about OpenStack Networking.
Thank you. So thanks for staying for the last talk of this conference. My name is Yves Fauser. I won't try to spell out my title that they gave me. I'm a networking guy working at VMware, and I have the pleasure to not only work in the pure VMware stack, but also to do a lot of things with OpenStack, and no matter if it's with or without hypervisor called vSphere. Okay, so what I think is happening right now in the network industry is kind of the perfect storm. There are so many things coming together that change the way networking is done and disrupt this pretty much stuck market. And a couple of very important pieces of this perfect storm are listed here. One is Open vSwitch, the other is OpenFlow /SDN, and the third one is, I would say, cloud platforms, OpenStack being like the most popular one. So Open vSwitch is a very feature-rich vSwitch for Linux, and it works equally well in KVM or Xen environments, and it's part of the Linux kernel since 3.3, so it's there, you can use it, and it has a couple of advantages that I will explain a little bit later. And if you combine Open vSwitch with, like, let's say, OpenFlow constructs, so SDN constructs where you have a controller controlling Open vSwitch, you get this power of like distributed networking through vSwitches controlled by a central entity, and I'll explain that in detail. And there are a lot of open source, but also commercial projects out there building these controllers that use OpenFlow to control either physical switches or vSwitches or both. And then we have OpenStack, or cloud management platforms, or whatever you're looking at in general, that drive the need for a more dynamic, agile way to build up networks. So the time is over where people are like happy to just wait for a week for a new VLAN to be configured on their network, right? So that's what we need to solve if we go really into cloud management and automation. We want to be able to automate the creation of networks the same way we automate the installation of packages on servers. Okay, so let's talk about Open vSwitch first. So that's more of a reference slide. What I want to show you here with that is a lot of the things that Open vSwitch brings natively is something you could already do with Linux Bridge in some way or form, with some projects, with some installations that you do yourself. The good thing is, with Open vSwitch, it's all native, it's all part of one configuration database that you can speak to centrally, and that's the big difference. The external management interfaces being OpenFlow and OVSDB, that's key to Open vSwitch, that you are able to control it from the outside much better than you are if you're using Linux Bridge with all those separated projects. The multiple tables forwarding pipeline and flow caching, that's a little bit difficult to explain. I guess in the demo it will be a little bit more clear, is one of the main advantages that you can spell out of Open vSwitch, and there have been a lot of performance improvements too. One of the most important one being receive side scaling support, so that on the inbound side you don't just send every packet to just one CPU core, you spread it out over the cores. Okay. How does Open vSwitch look like? So there is a kernel module of Open vSwitch, and there are user space daemons. The most important ones, OVS vSwitchD and OVSDB server. OVSDB server holds a configuration and state database. So you speak over like some management interface. Well, in this case, I'm showing the CLI interface. So you log into that server, you use the CLI interface, you speak to the OVSDB server, and it then pushes the configuration and all the state that you configure into the switch into this local config state database. And then you have the flow interface that you can also CLI to, and you type in what flow you want to build up. So flow being this VM can talk to this VM. So you would program a flow into the vSwitch saying that MAC address and that MAC address can speak. Let's put it really easily, right? Now, those user space daemons speak to the kernel module in the following way. We have in the kernel module what we call flow tables. And those flow tables, if you don't populate them, or if they're not populated yet, are just empty. And as soon as traffic comes in to the flow table, the kernel module will ask the vSwitch daemon, hey, do you know about that? Do you have a flow for that, a so-called macro flow? And then it will answer, yes, I know that flow, and you are allowed to build it up. So it's more or less like am I allowed to do this, or am I not allowed to do this? And if I'm allowed to do this, okay, we will have a caching here that enters this flow, this micro flow here in the flow table for a specific amount of time. And then traffic is flowing, and if it times out, it goes away again, etc. Now, we can also talk to OVSDB server and to OVS vSwitchD via external interfaces, and that's where OpenFlow and OVSDB as protocols come into the picture. OVSDB speaks to the OVSDB server over a protocol that is standardized. It's RFC 70 something. And a external controller can now speak to the OVSDB server and say, please build up those interfaces, or build up the logic on how those tables are structured, etc., etc. So you can completely configure the vSwitch from the external side through OVSDB. Through OVSDB, you can also get statistics, etc., etc. Now, OpenFlow is then used by the external controller cluster to speak to the vSwitch daemon here, and to program in the macro flows to tell the vSwitch what is allowed and what is not allowed. And then, again, you have the flow table or the kernel module integrating the vSwitchD. Okay, now common misconceptions regarding those controllers and the Open vSwitch is that every traffic will flow first to the controller, then the controller will do a decision and propagate that down using OpenFlow to the vSwitch. So that's a common misconception. And the answer is, it depends. It can be that way, but it doesn't have to be that way. In most of the architectures, we don't do that. We don't send traffic to the controller. So in OpenFlow, you can program a rule into the vSwitch or into the switch saying, please send me the traffic over the OpenFlow channel to the controller, and then I decide what to do with this flow, and I program it back into the switch. And that was mostly to address address space limitations of physical switches. Like low-end top-of-rack switches just had very limited space for flow entries, maybe 4,000 or something like that. So in a big network, you could really quite easily get to a point where you don't have any space in your CAM or TCAM to hold the flow entries that the controller programs. That's why some implementations with physical switches decided to send traffic to the controller first to decide what to do, and then to put in more specific entries into the vSwitch using OpenFlow. Now, in the case of the Open vSwitch, that's usually not needed. So with Open vSwitch, you have all the host's memory where you can hold all those flows. So we usually don't send anything to the controller in environments where we control Open vSwitch. Okay? And the second misconception we often have is that the controller is a single point of failure. That is interrelated to the first one. Like if you send traffic to the controller, of course, it would be a single point of failure. So yeah, depending on the architecture, even with a complete controller outage or controller cluster outage, traffic will still flow if you don't have an architecture where the first traffic will hit the controller. But we also have controllers that are usually built up in clusters. So some controllers choose a active standby model, but most of the controllers really have a scale-out cluster of nodes where the load is spread on those controller clusters, so the cluster itself, or the controller cluster itself, is highly available. And in the combination of both, having a highly available controller cluster and the fact that we don't really stop forwarding if we don't have a controller cluster, means that this misconception is simply wrong, or it's not relevant. Okay. Now, a little bit more on OpenFlow and controller-based networks. Now, SDN as a term is so overutilized and so wishy-washy, as we say in German. It really depends on where you come from and where you stand on what SDN is. And a lot of companies do what we call SDN washing. So they just take their general concept and say, hey, we did that all the time. We have a controller, we have some management functionality, program stuff into it. So that's SDN. Now, I actually don't really care too much, because there are so many environments, like in the wide area network, in the data center, in optical, etc., where this can be true or not. I think the most important piece is that we separate the control from the data plane. So in a standard switch, physical switch or router that we buy today, we usually have an internal interface between the control plane and the data plane. So the data plane is implemented in some hardware-specific way with some ASICs, etc., etc. And then there is an API inside the box itself that is closed, where the control plane that learns stuff like Mac learning, OSPF, etc., and then programs that into the physical hardware. What the concept in OpenFlow and SDN says is, let's separate that out and use OpenFlow to program those flow entries from an external controller cluster. And with this decoupling, the idea is we can build easy, not that expensive, off-the-shelf switches and have more intelligence and more agility in building new protocols, etc., in the controller. Again, that's all more or less religious debates. I just wanted to mention that so that you have like a clear view on where OpenFlow is actually used or not. Okay, there have been so many controller projects. I just listed some of them. You can go to that link if you want to have like a really, really big list of open source and commercial controller offerings. The most important ones being Knox and POX. Knox was the first one in the market. It's C code, and it was actually built, or the first parts of the code were built by Nicira that went then acquired by VMware, and the continuation of that controller is what we have at VMware with NSX. So the commercial offering of Knox is NSX. POX is a like port to do the same with Python. Then there is Floodlight. Floodlight was mainly done by big switch engineers and then open source. It's Java-based. It's a continuation of Beacon, which also came out of Stanford, and has a lot of concept around apps. So you have like your networking apps talking to some controller code that then programs stuff into switches or into vSwitches. Floodlight is still a very, very active open source project, and the continuation of that, or like the commercial offering of that, is what Big Switch does with their Big Switch network controller, or Big Network Controller. And then there is the new project called Open Daylight, and Open Daylight is this sentence comes from the Open Daylight website, is a community lab open industry supported framework. Actually, it's big companies like Cisco, IBM, etc., that came together and said, okay, how do we build such a Java-based controller? Who has what code, and how can we put that together to offer something in the market? And the first release of Open Daylight just came out, I think a month ago or 2 months ago. And well, there is a lot of drive behind that. Also, we at VMware are contributing to that project. So if you want to play around with open source controllers, I would say look at one of them, right? Not just an Open Daylight, which is certainly an interesting one that is backed a lot by industry, but look at all of them. Okay, now network virtualization is what I would call one of the SDN applications. And what we do with network virtualization is we take the vSwitch in the hypervisors, we usually control it by a controller cluster, and then we instruct those vSwitch in the hypervisors to build up dynamic tunnels through the physical network. So the controller cluster we are speaking of here is not speaking to the actual physical switches, it's only talking to the virtual switches, in this case Open vSwitch. And it's interesting in instructing Open vSwitch to build up something like a GRE or VXLAN tunnel between the hypervisors to transport traffic. And with that, we can build up a lot of virtual networks. We have a big ID space of 60 million IDs that we can use, and we can overlay a lot of virtual networks on top of the physical network that actually doesn't need to be configured for that. So the only thing the physical network needs to do is to route IP packets between the hypervisors. And then at some point, of course, we need to get out of this virtual world, and that's where we have gateways that do routing or bridging out to VLANs and to the wide area network that maybe or maybe not use dynamic routing protocols and announce those subnet, etc. So that's the basic concept behind network virtualization. There are some vendors that say network virtualization is also the combination of flow entries in the physical fabric and in the vSwitches. So you have the vSwitches in the hypervisor sending some tag to the physical switch, and then the physical switch uses another tag to build up the virtual network inside of the fabric. That's just another incarnation. There are a lot of proponents of the pure overlay, like MAC in IP, like we do at VMware and in other companies. And there are also other companies that, like Cisco with ACI, that say, no, the right approach to do that is to use a combination of flow entries into the physical switches and into the virtual switches. I'll leave it up to you to decide what the right thing to do is. Okay, so what's the technical definition of network virtualization? When can we really speak about network virtualization? So first of all, if we reproduce the physical network, if for the VM instance, the networking connections between those instances feels like being on a physical network. So broadcast and multicast work totally the same as they do in a physical network. Then they should be fully isolated. So we can reuse the same IP addresses over and over again. They can overlap. We can reuse MAC addresses. Those are really then completely separated constructs that we transport over the physical network. They should be location independent. So we shouldn't care about where the VM is in the physical network. And if two VMs or instances are in two different parts of the data center, separated by layer 3 routers, they should be able to communicate over layer 2 just as they would be connected to a physical switch in the same VLAN. And if we move them from one location in the data center to the other, with something like a vMotion, live migration, whatever you want to call it, it should just work. We should not need to have to configure a VLAN that spreads around rack rows and that break the physical design or the layer 3 design of the physical network. And what we say, what network virtualization is not, is it's not just running network functionality in a virtual machine. So it's not like having a router just in a VM form factor and then send traffic to it. That's not what we understand. What we say is network virtualization. Network virtualization is all what we have above there. Okay, now to OpenStack. In OpenStack, we have separated sub-projects that all have their own contributors group and their own project technical lead. And well, we have all these projects. I won't go into detail of what those do. In this talk, the most important one for me is Nova, which is the compute piece. It's where we schedule instances to run on a specific hypervisor using some interface, like if we run on a KVM hypervisor, libvirt, right? So Nova has a driver for KVM that talks to libvirt and places a VM on some KVM hypervisor, or an instance on a KVM hypervisor. And then we have the Neutron project that provides the network connectivity for this instance. So Nova and Neutron work together to provide the network connectivity for an instance. Some of you might have heard the name Quantum before you heard the name Neutron. It was actually called Quantum before, but then the Quantum Corporation sued the OpenStack Foundation for using this name, and so the whole code and the documentation, everything had to be changed to Neutron because of that. Okay, there was a networking solution before the Neutron project was started. And before the Neutron project was started, the networking piece was part of Nova, part of the compute piece. Same hold true for the volume piece that was then moved to the Cinder project. And we already had like the base concepts that we know also in Neutron, having base layer 2 provisioning, having an IP address management inside of OpenStack in an SQL database, using DHCP and DNS mask entries to provide the IP addresses to the instances, and using IP tables to do the netting and policing of traffic with security groups, etc. So that all existed before, but it was really limited to some easy going, let's say, network models. One is the totally flat network model, where you just patch an instance into a physical network, directly bridge out to one of the interfaces of the hypervisor without doing anything else. That is, of course, not multi-tenant. It just works then with security groups to provide isolation between the instances. Then we have flat DHCP, where we also offer a DHCP server to the instances so that they get the IP address via DHCP. And then the most used one was VLAN based. So every tenant gets a separate VLAN and has DHCP running in there. Now that means every tenant. So for a tenant, and that's one of the limitations that Neutron addressed, for the tenant you can't really configure multiple networks per project. So a tenant has a so-called project where he can start his instances. And in Nova networking, you could only have one single VLAN, and you could not dynamically configure additional networks. You could not configure routers, and you could not use all these advanced Open vSwitch features that give you the possibility to do network virtualization. So this whole tunneling approach of building dynamic tunnel overlays is not something you could do with Nova networking. And we also had the limitation of the VLAN ID, etc., etc. So that all led to Neutron. And what Neutron did, I have to go back once more. One important point was also the closed solution aspect. So Nova Network was not really easy customizable to have connectors, drivers, or whatever to implementation specific details. So if I don't know, we as VMware or Cisco or whoever, some open source component wanted to do some special source to build up those networks, we would have to really go into the Nova code and change a lot of stuff. So it was not really pluggable. And that is what Neutron gave us. So in Neutron, we have the concept of the Neutron server. And the Neutron server is what exposes the API northbound and gives you an abstract model on how to describe how to build a network. So you tell Neutron server over the API, I want to have a network. And you don't tell it, I want to have a network on that switch, and you have to do that CLI to do it, right? That's what we do with the plugins. So the Neutron server then speaks to the plugin to a so-called, Neutron plugin, and that Neutron plugin now knows what it takes to build such a layer 2 network. What do I need to do? If I have a physical fabric, I might have to build, I might have to configure the physical fabric for the VLANs. If I use an overlay, I might have to instruct a controller to build up a dynamic tunnel overlay. And that's what happens in the plugin. So a vendor or an open source project contributes a plugin to OpenStack, and then that does really the implementation into the physical world. And we have an extension, so everybody can build extensions, and at some point in time we might decide to also merge that to the core API. But as long as it's not merged to the core API, it's still technically going through the Neutron server, but it's directly speaking to the plugin, and the Neutron server itself just relays those calls to the vendor plugin. Then there is core and services plugins. So the Neutron server will now get those calls to build up a layer 2 network, to build up a logical router, to build firewall rules. And one possibility for the people that write the plugin is to just do everything in one plugin. And the other possibility is to combine those plugins. So a core plugin could offer the core functionality layer 2 networks, it could offer layer 3 routers, but then you can combine it to offer firewall or load balancing as a service features with another plugin, maybe also from different vendors. So we could build something like the core plugin is a plugin that does overlay networks with VMware, and the load balancing or firewall plugin could be something that speaks to a physical load balancer, Embrain or something like that, that have a services plugin for that. So to just show you how this is actually configured, we have the Neutron configuration, and there we can say where is the location of the core and services plugin. And in the services plugin, it's actually a list of plugins you can give, and that just translates into the right path where you have the Python code that then speaks to the actual physical implementation, that has the logic on how to speak to, I don't know, a load balancer of whoever. Okay, then there is the ML2 project. So one of the challenges that was introduced through this plugin concept is that a lot of this work that the plugin has to do, like IP address management or the ID management of VLANs, ID management of VXLAN, etc., was repeated over and over and over again. So every time I build a new plugin, I had to implement those database functions. And that's kind of wasted work for a lot of developers. So the idea was let's build a modular plugin. And instead of building one, what we now call a monolithic plugin that does all the work, we'll just have what we call now type managers and mechanism drivers. Type drivers and mechanism drivers controlled by the type manager and the mechanism manager. So type drivers are drivers that handle the ID space of a certain protocol. Like for VLAN-based networks, it would handle which tenant gets what VLAN from ID, 100 to VLAN 2000. So I'll tell ML2 to handle VLANs from 100 to 2000. And same for VXLAN, etc. And then on the physical implementation, I might have nodes that speak to a physical Arista switch, or other nodes that speak to a Cisco switch. And since we now separated out the ID from the physical implementation on what this means for an Arista switch or what this means for a Cisco switch, we can very easily plug in different modules together and have a common way of giving IDs to them. And yeah, up there we also have the database implementation that doesn't need to be repeated. Now, not everybody is really building mechanism drivers, because at the moment we're just in the phase where we start to deprecate what we call monolithic drivers into this ML2 pluggable framework. And a lot of companies, like also ourselves, have a lot of stability in their plugin code and don't want to just switch over to ML2. So we are a little bit We have both, basically. And it's not wrong to take one or the other approach. Okay, just a little example for you how this separation of type drivers and mechanism drivers is done. Okay, some of the plugins in the market. With ML2, we have plugins to speak to Arista, Cisco Nexus switches, Hyper-V agents, Linux Bridge, an Open vSwitch, and TLF and NCS is actually a controller-based solution. We have the classical Open vSwitch plugin and Linux Bridge plugin, and they are both being deprecated in the next OpenStack release, which is Icehouse, and then in favor of ML2. So ML2 will do all the work that these plugins did before, and they are deprecated. Then we have plugins like the one from VMware, the NSX, or also known as Nicira MVP plugin. We have a Cisco plugin that speaks to Nexus 5000 switches, etc., etc. So I'll leave it for you to read this list and to check out those links. There are also already load balancing as a service plugins from A10 and Citrix. And this is what comes with Icehouse, a lot of new ones, including a mechanism driver for Open Daylight. So that's with the Rio controller that we saw before the first time, we can really combine OpenStack neutron networking with an open source controller. So that might be interesting to also look at. And a lot of others. Just check out the link. Okay, so how does the open source implementation with the Open vSwitch agent look like, and how does it work actually? So we have the Neutron server with either the OVS plugin or the ML2 plugin with the OVS mechanism driver. And that one speaks to agents, being the Neutron Layer 3 agent, the Neutron DHCP agent, and Neutron OVS agents that are running on like all of the boxes. Or let's say the Neutron OVS agent is running on all of the boxes, and the DHCP agent and Layer 3 agent and Neutron server usually is running on one, what we call an OpenStack network node. Now what happens is that the Neutron OVS agent gets instructed by the plugin to build up specific interfaces and build up specific flows through a CLI interface. So the open source implementation doesn't really use a centralized controller to do that. It just uses calls over the message bus, so something like RabbitMQ, to talk to these agents and to build up these tunnels locally through CLI commands. And then after we plugged in the VMs to specific interfaces here, to the tunnel interfaces, we can use something like GRE or VXLAN to build up our overlay tunnels over the physical network. And then on the network node, what we do is we patch those interfaces to DNS mask processes, or we patch those logical networks to DNS mask processes to give the IP addresses to the VMs. So the first thing that happens actually that DNS mask is started, is patched to that logical network. Then the VMs come up and get an IP address. And what we also can configure is logical routing. That's the Layer 3 agent that does this. And that one builds up namespaces and IP table rules to do the routing through this network node. And the network node then patches this routing namespace between the logical network on one side and the external router interface to the physical network on the other side, so that we can route out or NAT out to the physical world. What else? One important point. What I could not show really on this drawing, because it would be too complex, is that this VM is actually going through IP tables, EB tables also, to do the security group isolation. So I configure a security group saying this VM can only be reached inbound by TCP port 80 or whatever you configure, right? And that is done also by the same agent here. It's then putting entries into IP tables, EB tables, and loops this virtual machine or this VM interface or instance interface through EB tables, IP tables. Okay. Just as a comparison, what would a controller-based solution look like? This is what we do. Other controller-based solutions would look very similar, I guess. Neutron server would speak to the plugin that speaks to the controller and would then instruct the controller cluster to build up this dynamic tunnel overlay. And as you can see here, we now don't have this OVS agent running on all of the boxes because it's the controller that speaks with OVSDB and OpenFlow to those vSwitches to instruct them what to do. So now we don't have this, let's go back, this local agent speaking over message bus. We have a centralized controller architecture. That's the main difference. And then we also, now in our case, we also have a layer 3 gateway. It's actually a gateway cluster that then handles all the layer 3 routing instead of the namespaces. But again, that's all implementation specific. That's what we do. And other controller-based solutions look quite similar. Okay, and now to the demo. I'll just pause for a second and hear if there are any questions before I go to the demo. There's a mic coming.
Hello. Can you tell us something about the production readiness of the Open vSwitch implementation of the open source solution you just showed to us, and how will it scale, let's say, for a cluster with about 200 computing nodes?
Production readiness. Let's put it that way. Most of the bigger installations are not using the open source implementation, but are using some form of vendor plugin. But usually with OVS. And there we have installations with thousands of nodes, being like companies like Rackspace, etc. The open source OVS implementation has some points like the way it handles flooding of broadcasts and multicasts that make it like not that big, not that scalable. Let's put it that way. There are projects inside of ML2 to have a local ARP proxy and stuff like that to reduce the flooding. But still, let's say mileage might vary, and we don't really have a big number of references actually using it in big scale. The references in big scale are using commercial implementations. Okay, nothing more? Okay, then let's go into the demo. So this is the OpenStack dashboard. And before I go into building up networks, etc., let's go onto the controller and look at the agents. So that would be Neutron agent list. So those are the agents I spoke of. The layer 3 agent, the DSCP agent, and then the Open vSwitch agent. We have one layer 3 agent, one DSCP agent on one central network node. And we have 3 of them on the controller that also does the networking function on the compute nodes. So the controller networking node is, of course, handling the patching into the DNS mask processes, and therefore it also needs an OVS agent to speak to the local OVS installation. Okay. So now we'll go to the Networks tab. And at the moment, we don't have a network defined. And I'm lazy. I'm using the Horizon dashboard. I could also use the CLI, of course. So I'll call it internal network, and I'll give it a subnet. And then let's give some IP addresses, whatever. That's my standard here. And we'll create it. So that now created this network entry in the database, but it actually didn't do anything else and just created in the database, actually. So before we go into starting a VM, let's have a look at OVS, and let's look at the tunnels. So this is what the tunnels look like. I'll just show the tunnels first before I show the other stuff. So those 2 ports here are being created by the OVS agents, and every time a new OVS agent comes up, we pre-populate those tunnel entries. So every time we have more and more tunnels, the more and more agents we have. And what we see here, I'm using GRE and not VXLAN, but just because I use GRE. And that's the remote and the local IP. And this key here, out key and in key, are actually keys that get populated by the flow table depending on the tenant or on the network in the tenant. So that's in another table where I see what logical network actually is what flow key. Okay? And that's all just patching logic. I have a really big set of additional slides in my slide set. So if you want to look at them, it shows everything that's showing this demo as kind of screenshots or copy and paste from that with explanations. Okay, so that's what it looks like, and that's on the controller node, and of course on the compute nodes it looks the same. And there we also have our tunnels. Okay, so the logical network was created. Next thing we do usually is to create a security group. I actually already configured a security group called allow all, where ingress I just allow all, right? I didn't fancy to build up really rules with TCP port 80 and SSH or something like that. Okay, now let's start an instance. A tiny one, and I'll just use zeros. Then here I select the security group. I could inject a key, an SSH key, so that I don't need to use a password. That uses actually metadata networking, but that would be too complex to show that in this demo. And now I just take the internal network that I created right now. So that is building now. And the first thing, as I said, that will happen is that we will build up a DNS mask process in the namespace. So if everything goes well, I should have a namespace here. That's the DHCP server handling the requests of the machines. So I can go into that namespace. And do an IP address. And there I can see that I have an IP interface 10, 12, 13, 3 for this DHCP server handling the DHCP requests from my instances. And if I look into that, yeah, always the same. I'm using a real Mac keyboard at home, and then if I'm on the mobile version, I always get that problem. So here we can see the DNS mask process that was started, and we can see that we patched it into, wait a second, bind interfaces. Here's the bind interface. And that's the interface tab 81 something. So if we do an OVS VSCTL show, we will see this tab interface. So that tab interface is now patched into my logical switch. The flow table where this is patched to will say some key that is identifying the logical network. And now if we look at the config file or the host file of that DNS mask process, we can see that we now only have one entry, which is the entry for the instance that I just started. Okay? So that is active and running. I'll launch a second one. If you have any questions, please interrupt me while I'm speaking. I'll launch it. Okay, and the next thing we'll do, let's see, now we have two entries, of course. The next thing we'll do is we will configure a router in that network. So we'll go to the routers tab, or we could also create it using the CLI, and I'll just call it my router. Again, that just creates an empty router container as soon as I set a gateway, and here I pre-configured an external network that connects the router to my Mac, right? It's all running in my Mac as virtual machines. So now the router is actually connected to the logical network on my Mac. And the next thing I need to do is to add an interface into the internal network. And voila, I build up my router. And we also have a nice topology tab on the Horizon dashboard that now can show us, or shows us how this actually is connected. So here's my internal network with my instances connected to this router, and I see all the IP addresses that were given to it. Okay, so what does this router look like on the box itself? That's actually also a namespace, as you might have guessed. And we can go into that namespace too. Oh, you're right, sorry. And now I see the router IP address 10.12.13.1. Now the last validation step, of course, is to connect to that instance and see if it works. So it got its IP address, and I should be able to ping the other hosts. I think .4 was the other one, yeah. And that now travels over the GRE tunnel. Actually all in my Mac, but yeah, just imagine there would be switches. Okay, what else can I show you? That's pretty much it. The last thing I could show you is I could map a floating IP. Floating IP is just a NAT, a source destination NAT entry. By default, what we do in neutral networking is that every network that gets connected to a router, all the instances in that network are source NATed to the router IP. So everything inside of the tenant can go out. And floating IPs are actually combinations of source and destination NAT rules to make it to make a specific instance inside of an internal network available through an external IP address. So that would be my external IP address that I allocated to my project, and now I'll associate it to a port, which is the port of my test instance 1. And now I should be able to SSH into it. Yes. Okay, and I'm connected to it. And if we look at the router namespace again, now we see that we have an additional IP address, which is the floating IP. And we can also look at IP tables. And there we will see, first of all, no, sorry, that's the wrong output. IP tables minus NAT, I think it's. Nope. Then TNAT, thank you. Okay, that takes a while. While that is happening, I can go here into the compute node and do what I wanted to do here. And here you can see that we have some entries in IP tables doing the security for the instance itself. So the first entry we have here is a entry that maps the MAC address to the IP address. So if somebody would give its instance another IP address than the one we assigned through Neutron, it would actually not work. So it would drop it. Kind of a security prevention. You really have what we call port security by default in OpenStack. And then up here you have the inbound rules allowing TCP traffic, ICMP traffic, etc., etc. So that's how it is implemented in the OVS agent version. In controller implementations like the one we have, it's actually different. There we configure specific flow entries in the vSwitch instead of using IP tables. Okay, and here are the NAT entries. First of all, the source NAT root for the whole subnet, and then up here the destination and source NAT rules for the instance. Okay, and that basically concludes my demo. Any questions? You tired? Okay. Then, thank you and have a great return to wherever you go, or maybe a good puppet camp tomorrow.
Thank you very much, Yves.